Hi everyone, I'm Ritabrata Chakraborty. Today I'll present our work, a transformer-based handwriting recognition system jointly using offline and online features. This work is a collaboration between Manipal University, Jaipur, Indian Statistical Institute, Kolkata, and the University of Salford at Manchester. For handwritten text understanding, there are two possible modes of input, of strokes and images. Strokes are pen sequences of X, Y, and pen up or down, while images are pixels of the glyph. The images capture texture, shading, serif shapes, basically appearance, but they lose temporal order. Strokes, on the other hand, capture pen dynamics, that is how the character is traced, but they lose appearance details. Hence, each alone are brittle under writer variability. Hence, offline, denoted as figure A, and online, denoted as figure B, pipelines, are not robust enough. Recent literature has addressed fusion of strokes and images through works like OLHDR, where efforts were made for late fusion, where encoders run separately and only merge near the classifier. However, this limits cross-modal alignment and wastes synergy between images and strokes. Hence we ask, what if we could have early fusion that puts stroke and image features in the same representation space? This is denoted by figure D. What if we project both modalities into the same token space early and let them attend to each other before the task-specific layers? To this end, we introduce ACPR classifier. We tokenize image patches and stroke points into a shared latent space. Learnable latent queries first absorb image tokens, then stroke tokens query those latents via cross-attention. Finally, attention pooling feeds a linear head. This early fusion lets the network learn shared primitives, like a cusp, being both a sharp curvature and a dark pixel cluster. Thus, we can utilize the interaction between how a character looks in pixel space and how it is traced through the pen vectors. We present the HAT algorithm. Operationally, we encode image patches through a SwinB backbone into tokens. Then, we build a small transformer for strokes with rotary position embeddings. Finally, we run latent cross-attention on image tokens, and then conduct cross-modal querying where strokes attend to latents. Finally, we attention pool and classify with cross-entropy. Hence, our network can handle image only, stroke only, or both, without any parameter changes. For our experiment setup, we train and test on three datasets: English IAM on DB, Vietnamese VN on DB, and ACPR numerals. Our metrics include accuracy, precision, recall, and F1. We further also run ablations and convergence feature extractors and the importance of early fusion. As is shown in the table, we achieve state-of-the-art result across all datasets. On IM on DB, we edge past strong baseline of HDR-VT. On VN on DB, our dual mode outperforms the stroke-only mode, showing that early fusion resolves this stroke ambiguity. And on ACPR, we also surpass prior RNN LSTM results. We show some qualitative results. Green labels show our correct predictions where baselines misfire. Even without word context, early fusion stabilizes confusing characters, especially where diacritics or subtle curvatures matter, like Vietnamese stones or similar-looking Latin glyphs. We present some ablation studies that reinforce our contributions and as to why early fusion matters. We present some key findings. For the figure on the top left, we find out that SwinB trainable gives the best trade-off, and freezing hurts 10% on IM on DB. It is important to note that all ablations here are shown on IM on DB itself. Table 5 shows us the fusion level comparison of models on IMONDB. We see that early fusion outperforms middle and late fusion, confirming that aligning modalities before higher level reasoning is best. Also, a single dual trained model degrades gracefully if one modality drops at test time, showing around 4 to 7% loss only, as shown in Table 6. We also display accuracy versus convergence for models. Following are the limitations and the future work in this thread of research. Our current system recognizes isolated cliffs and depends on a training visual backbone of 90 million parameters. Performance has also not been audited across writer demographics. The figure on the right shows some limitations or failure modes for our scenario. Hence, future work lies in curation of a large level multilingual word level and line level dataset to extend the usage of this framework to real applications. There is also potential in providing for manually segmented character information that might help in better benchmarking results. We open the floor now for any questions around our work. Thank you.